Okay, another Poisson type problem. Let's suppose we've got two editors or writers of a manuscript. You've got writer A and you've got writer B. Okay, suppose A makes errors, typically 2 per page. So this per is really trying to suggest to you that this is a rate, okay, which is really trying to suggest the Poisson distribution. Anytime you see the word per, often you will be talking about the Poisson distribution. A second writer, B, they also work on the book. He happens to make errors at a different rate. Okay, so she makes 2 errors per page typically. He makes 3 errors per page typically. Okay, so let's say that person A wrote the first 100 pages of the book. Person B wrote the last 100 pages. After the book's completed, find the probability. You find that the text has a total of 520 errors, regardless of the first or the second chunk of pages. Well, let's write a formula for the exact probability that fewer than half came from person A. Okay, so here it says exact probability. Originally, I'm going to solve this using the Poisson, which will not give us exact probability. The binomial will give us the exact probability, but first I'll use the Poisson, then I'll use the binomial. Okay, so what I'm going to do here is reparameterize these two people, their error rates or their success rates, whatever you want to call them. Person A typically was said to have 2 errors per page, and here I'm just going to multiply that by 100, which would mean in 100 pages I would expect 200 errors. So I've just multiplied everything through by 100. Then X is the number of errors from A in the first 100 pages. So this will be a Poisson with lambda being 200. Okay, for the second person, they usually make 3 errors a page. Again, multiplying by 100 because they wrote actually 100 pages. Then their error rate is 300 errors per 100 pages. Y is the number of errors from B in 100 pages, and it will be modeled by a Poisson distribution. Okay, if there were 520 errors in total, then we know that X, the number of errors from A, plus Y, the number of errors from B, must equal 520. Okay, we're wondering about fewer than half coming from person A. Okay, so what is half? Exactly half of the errors would be 260 errors. We're trying to find the probability that person A made less than 260 errors. Okay, so let's write this out. Again, person A could have, it's possible, they could have made 0 errors all the way to all 520 errors. The reason why Poisson is actually approximate is because really Poisson goes off to infinity. Here we're saying there were apparently only 520 errors. Apparently we know that. How we know that I'm not quite sure, other than the fact that it's told to us. But if we assume the number of errors could be infinite, that would be exactly Poisson. This is only approximately Poisson because it actually, apparently, we know the exact number of errors. So what's the probability of X, which is the number of errors from A, being less than 260? Now be careful, okay? Because it says what's the probability of fewer than half the errors? Okay, so we can't say that A has made exactly half. It says fewer. That is strictly less than 260. Okay, which of course, here's 260. We're not including 260. We're saying anywhere from 0 to 259 errors. So less than or equal to 259 errors. Okay, so here A's lambda, their error rate or success rate, whatever you want to call it, is 200 errors per 100 pages. What's the probability that they made less than 259? Let's see. Calc probability distribution, this is a Poisson. Here the number of errors they typically make in 100 pages is 200. What's the probability that they made actually less than 259? Okay, anywhere from 0 to 259 errors. And the probability of that happening, that they made less than that many errors, that many or that less, is very high, very large probability that A made less than or equal to 259. Okay, so person A really only typically makes 200 errors. What's the chance that they made less than or equal to 259? Well, very high chance they didn't make this many errors, okay, or less than or equal to that many. Okay, if we wanted to find the exact probability, again, Poisson's a good approximate, but the issue here is that Poisson truly does go off to infinity, whereas really we have a known number of errors. Okay, so when we have a known number of repetitions, this is actually the binomial distribution. So let's rewrite things. Let Z be the number of mistakes made by person A. Okay, out of the 520 errors, and we know that the probability of A making a mistake, well, typically they make 200 out of 100 pages. And here, 200 divided by the 200 they expected to make plus the 300 that B is expected to make. Okay, so this is just 200 out of 500, which is 0.4% if you look at any error that it actually came from person A and not from person B. Okay, what this means is person A makes mistakes 0.4 of the time. When you're considering the mistake, whether it came from person A or person B, 40% of them will come from person A, 60% of them will come from person B. Okay, so there are two possibilities, make an error or not. The number of errors is known, it's 520, and the probability of making an error here, if your person A is 40%, if your person B is 60%. Then Z, of course, is a binomial with the number of reps being 520, and the probability of it being person A's mistake is 40%. Again, fewer than 260 would be less than or equal to 259. Okay, so fewer than half, not exactly half, but anything fewer than half. This will be the probability of Z being less than or equal to 259. Here, this question asks you to write it as an exact probability formula. Okay, so write the formula. So I do write the formula. I know that the binomial formula is the number of reps choose the number, probability of success to that number, probability of failure to the remaining number. But here, of course, I need to sum up from 0, 1, 2, 3, all the way up to 259. I can use the summation notation to do this. Here I'll let let I be an index. It'll start from 0, so originally I'll plug in 0 where I is, and then I will add it to here I'll plug in 1 wherever I is. And then I'll go to 2 wherever I is. All the way up from 0 to 259 with the summation notation. This is how to write the exact formula. Of course, using Minitab to do this, then we can say this is calc, probability distribution. Here we're talking about a binomial. We want a cumulative probability where the number of trials was 520 and the probability of success apparently was 0.4. And I want to do less than or equal to 259. What is the probability of all of these things added up, or what does this equal? Here we ask Minitab, which because of rounding has just rounded it to 1. Okay, it must have been very close to 0.999999999 whatever, and so it rounds up to 1. This is approximately 100% chance that person A makes less than or equal to 259 errors. Okay, so very, very, very likely that person A has made fewer than half the mistakes.